Okay, so we've started to look at radial fields. We've looked at Coulomb's law and we figured out the force that would act between two charges which have a radial field, point charges. So the next job is to look at electric field strength in radial fields. It's going to behave in a slightly different way to how it behaved in uniform fields. Well, let's remember the definition first of all. Well, electric field strength is the force per unit charge. And of course, we decided that it's always true to say that electric field strength is this vector quantity, is the force per Coulomb that would act at a point. And it's an important point to realise that field strength, electrical field strength, it's a property of a point in space. So in other words, it's the force per unit charge that would act on a charge if you put it there. Yes, that's the idea. So if you have an electric field, then the field strength exists, and if you then put a charge there, it's going to feel a force accordingly to its size. Okay, well, we can make a little bit of a head start here of finding out how to determine the field strength due to a point charge. The question is, what is the field strength due to a point charge Q1 at a distance from R from its centre? So let's draw it. So there's some charge Q1, bang. And so the question we're asking, what we want to try and find an equation for, is what would be E, what would be the value of field strength E at distance R from its centre? In other words, what would be the field strength at that particular point? And then we've got a general equation for field strength in a radial field. Well, we can do a bit of a trick here. We can actually just utilise Coulomb's law because to derive it. So remember Coulomb's law from the last section told us that the force between two charges was Q1, Q2 over 4 pi epsilon 0 or epsilon naught R squared. Now, what that means is then that if I came and put Q2 just there, a charge of value Q2, then we actually know the force that would act on it is given by Coulomb's law. This is a law that has been discovered by experiment. But that gives us a kind of way to kind of go backwards and find an expression for electric field strength, because we know that field strength is the force per unit charge. So I can say, electric field strength is the force per unit charge. Well, in this case then, we want to know the field strength due to Q1. Well, I know that if I put charge Q2 in the field of Q1, then the force on it will be given by this equation, Coulomb's law. And I want the force per charge, force per Coulomb. So of course I need to divide, that's the force on Q2 coulombs, so I need to divide by Q2 to get the electric field strength, to get the force that acts on each individual Coulomb. So what I do is I say, so the electric field strength due to Q1, let's write it like that, is equal to the force on Q2 in the field of Q1, which I'm going to write just as we had from Coulomb's law, divided by Q2, because that's the force on Q2, we want the force on 1 Coulomb, so we have to divide. So if Q2 was 5 coulombs, and we want the force on 1 Coulomb, we need to divide by 5, because the electric field strength is the force on 1 Coulomb. So look, if you need to pause and just listen through that again, do so, but make sure you get it, make sure you understand what I'm saying there, because that simplifies now, and we end up with E, the field strength due to in the field of Q1 is going to be equal, the Q2's cancel out, so we get Q1 over 4 pi epsilon naught R squared. Now, that is for Q1, but of course I can write a general equation for the field strength due to a charge Q. We've only got one Q in here now, so we don't need to put Q1 or Q2 or Q3 or anything. So I can actually just generally say, well, the field strength due to a point charge is the size of the charge divided by 4 pi epsilon naught r squared. And that is the equation. Now you do have to be able to derive that. So basically you have to be able to write those steps in an exam. Write down Coulomb's law, write down, well, field strength is F over Q, and therefore cancel out one of the Q's and get this equation. Good. Well, questions regarding field strength in a radial field are pretty similar really to ones involving Coulomb's law, because of course field strength is also the force, it's just the force that would act on a unit charge. So have a go at the questions that follow. Just before, just one other thing it's interesting to have a look at is the graph of what field strength looks like as you move away from the point charge. And typically, well, even if it's a proton, but certainly if it's a bigger point charge or something approximating a point charge, or it could be a charged sphere, there's going to be some surface, so there's going to be some radius inside of which we can't really sort of analyse, because there won't be an electric field, or there will be an electric field that behaves in a different way. We're only interested in the electric field that occurs outside of the sphere, from the surface outwards. So we're going to start at some position, and basically we're looking for a graph which is showing that E is proportional to 1 over r squared, and that, if you think of y equals 1 over x squared, well, hopefully you can see that it's going to be sort of some kind of shape, something like that. So in theory it goes on forever, and electric field strength does in theory have an infinite range and gradually tends towards the x-axis. This position here is the surface, I'm going to call it big R, the surface of the sphere or charge, which will be a distance big R from the centre. And so there's going to be a fixed value of E there. In fact, we know what it'll be. It'll be Q over 4 pi epsilon naught big R squared. Well, I hope that makes sense. Have a go at the questions and see how you go.